Hello and welcome to this, the first of 8 short presentations and lectures looking at the introduction to flow frequency part of the workshop. What we're going to do in this short presentation is have a look at hydrological time series. There are a few things that we're going to look at. We're going to look at ways in which we might measure river discharge. We're going to look at how we might relate water levels or water stage to discharge, how these produce flow time series. We'll have a look at one way of describing the data using flow duration curves, and then we will also briefly have a look at how we might decompose these complex time series to try to understand some of the processes that cause these patterns that we see in the data. Here are a couple of examples of river discharge data. Discharge here from going from 1 to over 1,000 cubic meters a second from the Arengay River in the Philippines. We've got data from 1985 through to 1997. We can see the wet season, dry season cycles here very clearly. Some dry seasons, very low flows, some not quite so low. We can also see individual events. This is daily data, so any high flows that last for a day will show up as these spikes. And we see some gaps in the data where the instruments weren't working properly and the data are missing. And that's a very common situation with hydrological time series. The other example here is just for illustration really, but it's from the River Nile in Egypt. And we've got data here from before 700 AD all the way up to 1400, and these are water levels. So this is the flood water level in the wet season, and here are the low water levels in the dry season. A very long time series, several hundred years of data showing some fluctuations that we might relate to climate. This increase in wet season heights, quite interesting in the 13 and 1400s. This does illustrate how useful these sort of river flow data can be. In ancient times, the water level that the Nile got to in the wet season was used by the government to set the tax. If the water level was high, then the soil was going to be very fertile, and so farmers would grow very good crops that year, and so the government set a high rate of tax. If the water level was lower, the crops wouldn't be so good, and so the rate of tax was lower. So you can see that there are many possible uses of water level recording and river discharge recording, as well as the sorts of things that we might be interested in predicting flood levels, for example. So how do we measure discharge? Well, first of all, it's reasonably simple to measure water level. We might measure water level visually. We might use something called a stage board, which is basically a ruler, which we mount in the riverbed, and we could read manually if we wanted to, the height of the water at any time that we wished. It became very common 20 or 30 years ago to use pressure sensors. We've got one of those in this tube here, a pressure sensor at the bed, and the pressure sensor measures the depth of water above it. Very easy piece of equipment to use, very reliable, and gives an accurate water depth value. On the other hand, more modern sensors, you tend to use ultrasound, and they don't measure the depth of water. They look down from above and they send out a sound wave which bounces off the water surface and tells you the elevation of the sensor above the water. And that's what's in this construction here in China. They have an ultrasonic depth or water level measurement device that points downwards. Those are very good ways of getting almost continuous records of water level. You can set them up to measure every 1 minute, 15 minutes, 1 hour, daily. Depends on how big your river is. Generally speaking, in smaller rivers, we would use higher frequency because the water level goes up and down much quicker in smaller rivers. In larger rivers, you might use a 1 hour or even a longer frequency of recording. If we want to get reliable results, we want a section to make measurements in that is straight, so the water isn't going around bends and doesn't rise up as it does so. We want the river banks to be stable, and we want the river beds to be stable so that we have constant conditions through time. You see this example in China. The river banks are very stable. They're fixed concrete banks, so we know there's not going to be any bank erosion. We can't see the bed, but we assume that the bed is quite stable. This project in Norway, we didn't have much choice. We had to make measurements where we could, and here the banks were subject to erosion, as you can see. The river bed was also somewhat variable. We had to keep resurveying the geometry over a few weeks because the riverbed kept changing, which is not ideal. We can measure the water levels relatively easily, but how do we convert those water levels to discharge? Well, we also need to do calibration. So we'll say a bit more about that in a moment, but we might use a flow meter like was being used here. We might use some dye and look at how quickly it dilutes. That's a very good way of doing discharge measurements in small streams. Or we might these days make use of an acoustic Doppler current profiler, which automates a lot of this process. And in the workshop folder alongside this presentation is another presentation, a PowerPoint presentation from Richard Williams that includes 2 short videos of ADCP gauging in action, and you can see how that works practically. The map here is a map of the Philippines, and Pammy is going to talk to you about this in much more detail in a later presentation, but it shows the location of all the gauging stations that we have data for our project. 3 different data sources in different colours, superimposed here against over the climate types for the Philippines that you might be familiar with, showing that we've got very good coverage, especially in Luzon, but also in some of the other regions of the Philippines. We've got good data coverage that we're able to use for our analysis. So the principle of calibrating between water level and discharge is that we need to convert a water level in meters to a water discharge in meters cubed per second. And typically we would use something called the velocity area method. So the discharge Q is equal to the mean velocity multiplied by the cross-sectional area. So in this top diagram, we can measure the area of the blue river channel. We can measure the mean velocity, we multiply those 2 numbers together, and that gives us the discharge. So meters cubed per second from a meters per second velocity and a meter squared area. Because the velocity varies across a river, it's not easy to make a single measurement of mean velocity. So a practical way of solving that problem is to separate the river into some slices. And we can do that with these vertical locations where we measure the water depth and velocity, separated into slices that have widths shown here, W1, W2, and so on. And we can measure the discharge in each one of these slices and then add up the discharges to get the total. So that Q total is equal to Q1 from slice 1 plus Q2, all of the way through to Qn minus 1 at the end here. The way in which the calculation works, we need the mean depth in that slice, which is H0 plus H1 divided by 2 for the first slice, and then 1 plus 2 divided by 2 for the second slice. We do the same thing for velocity. Take the velocity at the 2 edges of the slice, add them up and divide by 2 to get their average, and we multiply by the width of that slice. We repeat that for all of the slices, add them up, and we get the discharge. Where do we measure the velocity? Well, we don't measure the velocity near the surface, we don't measure it right at the bed. If we want to get an estimate of the mean velocity in one vertical section, we measure it at approximately 0.37 h above the bed, where h is the flow depth. In other words, 37% of the way from the bed to the surface. Theoretically, that's where the mean should be located. Quite often, to improve the reliability of measurements, we would take two values. We'd take one 20% of the way up, one 80% of the way up, add them up, divide by 2. And that, again, theoretically is the same as the mean at 0.37. So we can make those measurements individually using a flow meter, measure the depths using some sort of depth device, measure the width using a tape measure or a piece of surveying equipment, and we can get all of the numbers we need to put into here. If we do this using an ADCP, the ADCP essentially does the same. It does a numerical integration of measurements of depth and velocity to calculate the discharge. The software within the ADCP is solving this equation and putting numbers into that equation, but it's doing it almost continuously rather than in slices. The same approach, though, in order to get the total discharge. So after we measure discharge, we can then plot that against water level or stage. Stage is usually the word that's used. It essentially means water level. And we can plot discharge against water level, and we see here that we get, this is a typical set of data from the Power River, where we have a relationship that looks sort of curved when we look at it. Two things to note. We take a lot of measurements at low flows because that's where the flow is most of the time, and it's also easier and safer to make measurements at low flows. We don't have many points at high flows because they don't happen very often, and it's not so easy to make measurements under those conditions. So the data tends to be biased towards low flow measurements. Now, because this is a curved relationship, we will fit an equation to that data, which is of this form, a power law. So we relate the discharge Q to two constants. One is a constant here, C, that we multiply by. The other is this exponent K, which tells us how curved this relationship is. And in here, we also have the water level, H. We may need an offset because quite often the 0 point on your water level measurements might not be the lowest point on the riverbed. So sometimes we need to include an offset. Now, in order to make the analysis easier, we plot that on logarithmic axes. So now we have discharge against stage on log-log plot, and we see that that becomes a straight line. The points lie quite close to the line. Note that the high flow points are maybe a little bit off, but we don't have many up there, so it's a little bit difficult to be really confident in that. When we plot on log-log axes, the slope of this straight line is the exponent K, and the point should lie close to a straight line if the flow in the measuring section is uniform. If it's not accelerating, it's not going around bends, and also if our measurements are reliable. And as I say, at high flow, it's more difficult to measure at reliable measurements. In this example, 40 measurements were made between 1920 and 1922, so it's quite old data now. It's 100 years old. The value of C comes out at 8.06 with a very low error, so we're 95% confident it's between 8.04 and 8.08. The gradient K has a gradient of 5.21. We're not so confident here, 4.93 to 5.48. And that's partly because of these high flow points, which are potentially less reliable. In this case, there was no offset applied. So that's how we take our water level measurement, our stage, and convert it to discharge. We would use this equation, that equation, with these values plugged in to calculate Q for any measurement that we make of H. So doing that, we can then generate flow time series with discharge on the y-axis rather than water level. Remember what I said earlier, there are some gaps in the data where the instruments weren't working, so we have to remember that. But we can then summarize the data in a lot of different ways. And here are two plots basically showing the same thing, but just slightly differently. The top plot is the daily data. So on every day, the 1st of January, 2nd of January, what has been done here is to calculate what's the mean flow, which is the pale blue line, what's the median flow, the darker blue line, on each day of the year. And then the shaded areas are the ranges. The dark shading is the 25th to 75th percent, the slightly paler shading 5 to 95, and then the very pale shading is the maximum and minimum on that day of the year. And when you do that, the dry season shows up very clearly, flows getting lower down into March and April. Then we have the wet season, flows becoming quite consistent, certainly in terms of the mean, all of the way through from July to October, and then falling away again as we go towards the end of December. What we also notice from this is that we do see quite a lot of variability day to day because we're using daily data. And that can be quite useful. It gives us some indication as to, for example, here in late October, there was one year that there was quite a big flood, and that has an impact on the statistics. Actually, a lot of the time, this variation is a little bit noisy. We might want something a bit simpler to look at, a bit smoother. And here we can calculate just one value for each month, and then we can look at the variation but year to year between the values in January, values in February, values in March, and so on. And we see that here quite clearly, that we have the seasonality again being picked out nicely by this plot, but it's a much smoother overall relationship that we see. There are other ways of summarizing the data, and one very commonly used way is to use a flow duration curve. And a flow duration curve is a way of looking at the percentage of time that the flow is at different levels. So what we have here again is discharge on the y-axis, and on the x-axis we have the percentage of the time that the flow is at least equal to the indicated value. Now there's lots of different colours here for different months, but the black line here is the whole year data. So let's just look at the black line for a moment. So for example, the median value, the 50% value, if we read up here to the black line and then go across, we see that it's just a little bit below 10 cubic meters per second. So in other words, half of the time the flow is below 10 cubic meters per second, half of the time above. 10% of the time the flow is above this value here, which is about 250 cubic meters per second. So 10% of the time the flow is above that. And we could go to 5% or 1% if we wanted to look at the flood flow conditions. The different coloured lines are for different months. So the dry season months plot down here because the flow never gets very high. So this is March, the one right at the bottom. The highest flow is only about 2 cubic meters per second. So it's right down the bottom. And as we go from the dry season through into the wet season, the curves move up. And then in the wet season, they're above the annual average. So this purple line for October, and then we go up here July, August and September at the top. And so we can look at it month by month, and we can say, well, the 10% value in the wettest month is about 400, 500 cubic meters per second. In the driest month, the 10% value is at 2. So we get a sense of variability within the year from these curves. Often we will talk about percentiles, and because we're interested mainly in floods in this workshop, we're interested in the very low percentiles, the 5% or the 1% or the 0.1%. In other words, the largest events that we see in the record. So we can write these percentiles as Q99, flow exceeded 99% of the time, Q50, the median, the flow exceeded 50% of the time, and Q1, the flow exceeded 1% of the time. Just a reminder, that's 3.65 days per year on average, 1%. So it's a few days per year we're talking about when we talk about Q1. How are flow duration curves calculated? We don't really need to know how they're calculated because software does it for us, which is nice, but this just runs through how it works. For a start, we can use any flows. We can use daily, monthly, annual, and we'll get slightly smoother versions of the curves as we use longer averaging periods, but we can calculate them using different data sets. As I say, software does the calculations for us, but what the software is doing very quickly is it's ranking the data, usually from high to low, but it can be low to high, and M is the order, is the rank order of a point for a series of n data points. And then the probability, PR, that the flow is at least, in other words, greater than or equal to a specified flow, probability that Q is greater than or equal to QI, is equal to M, the rank, divided by n plus 1, where n is the number of data points. Those calculations are all done, and you produce the flow duration curves. Now, here's another example, this time from the UK, from the River Orkney in Scotland. You can see we have about 34 years of data. The instrument was working well 98% of the time, which is good. And then here we have the different exceedance values. And you can see what they've done here. They've plotted 3 lines this time, not every month, but they've plotted the overall average in black, the wet season, the winter in our case, in blue, and the dry season, which is summer in our northern hemisphere, temperate setting, in red. So similar to the previous example, but not using each month this time, now looking just at 2 seasons as well as the overall annual average. Flow duration curves are very commonly used, but we are really interested in these high flows. So in most of the analysis we're going to look at in the next few lectures, we're going to focus on analysis that tells us about these highest magnitude flows that only occur a few days each year. We might also want to look at some of the causes of that variability in a river flow. And one thing we can do is we can decompose the time series into its component parts. Time series contain quite a lot of signals all added up. There's a seasonal signal, a wet season, dry season signal. There are some trends which may be linear or might be more complicated than linear. We have events, we have storms, we have typhoons, we have dry periods. There are some measurement errors, and of course there are missing data. And we can use software to break that signal down into different components and look at them separately. So what we've done here is look at the data that I showed right at the beginning for the Arungay River. Here's the data. The y-axis is now in log units, so don't worry too much about the numbers, but here's the pattern of the data. Here's the seasonality, and we can see wet season, dry season, wet season, dry season, repeated based upon the average values that we found for each day of the year. Here's the trend. Now the trend is interesting in that not much seems to be happening, slightly up, slightly down, and then we get a big jump here. Now, if you remember that first slide, there was actually a gap in the data here, which has been filled in by the software, but the software filled it in a way that because the dry season was missing, the software didn't know there was a dry season. So it's filled the gap in, and it gives the impression that there's been a big peak in that year. So we have to be very careful actually with the missing data. So the trend picks out a wet year with no dry season, but that was due to missing data. So we'd have to be very careful how we handle missing data, and that's a subject we could pick up at another time if you're interested. What the seasonality picks out the wet season and dry seasons very well. The trend does show some possible real trends as well. There may be some slight increases going on in the last few years, from 1994 to 1996. It also allows us to see in this the remainder, the bit that isn't accounted for by the season or the trend, we can see the impact of individual events. There was a dry period here, that picks out very clearly. We had two separate peaks. Those both show up here. This dry season was unusually dry, and very low flows, and they lasted for longer than some years, so we get that picked up. These longer dry seasons get picked up here, whereas here we didn't have such long or so well-developed dry seasons. They're not picked up on the data. So the data is very complex. The seasonality is quite consistent year to year. The trend is interesting, but be careful if just to make sure missing data haven't affected the results. Then the remainder tells us about things we may not have picked up. Events, dry events, wet events. There are a lot of other ways of analysing hydrological time series, and we'll look at some of that analysis in the next few short presentations. For now, thank you very much.